first online lecture on dynamic programming here at the University of Copenhagen or wherever you are. So I regret that we have to meet like this. I really look forward to meet all you guys and take over from Thomas. But this is what we can do at the present state of affairs. So Tom has already introduced you to a bunch of theory of tools, and he used them to solve continuous choice models and also models combined with discrete choices. Now, what we're going to do now is we're going to go more in detail with discrete choice models, and we're going to focus explicitly on how to estimate models that involves discrete choices. The main topic for the lecture, the first lecture, is a paper by John Rust, Optimal Replacement of GMC Bus Engines, an Empirical Model of Harris-Zucker, that came out in Econometrics in 1987. In that paper, he develops the nested fixed point algorithm that's going to be our workhorse throughout this course that we will try to estimate dynamic discrete choice models with. So this is really the basic starting points for learning all about structural estimation of dynamic programming models. So this is why we have to read this incredible, nice paper. Anyway, my name is Bertel Channing. I'm a professor here at the University of Copenhagen, and I'm going to take you through the next couple of lectures on this course. So what I want to talk about here is just essentially the plan, and then in a separate video, I'll go on with the first lecture. So we're in part 3, so Tom has already covered part 1 and 2, theory and tools, and continuous choice models. So we'll focus on empirical applications of dynamic discrete choice processes. And the first lecture, the lecture for today, is about the nested fixed point algorithm, an algorithm that implements the maximum likelihood estimator that allows researchers to estimate dynamic discrete choice models with maximum likelihood. It's called the nested fixed point algorithm because there's a fixed point algorithm nested inside the algorithm that maximizes the likelihood function. So you can think of an outer algorithm that searches over the parameter space, while for every time you evaluate the sample criterion that you use in estimation, for instance, a likelihood function, you would have to solve a fixed point problem. And that's why it's called the nested fixed point problem, because the fixed point problem that you solve is nested within the maximum likelihood maximization routine. Okay. Anyway, I'll talk more about that in a second. I just want to give you here the broad overview of what we're going to do for the next couple of lectures. Next time, we'll look at another approach to estimation advocated for by Ken Judd and Shilin Su. It's a constraint optimization approach. So where the nested fixed point algorithm resolves the model for every evaluation of the likelihood function, the constraint optimization approach, which is also called mathematical programming with equilibrium constraints, or just short MPAC, really maximizes the likelihood function subject to a set of constraints, in this case, the Bellman equations. So you maximize the likelihood subject that the Bellman equation needs to hold using constraint optimization software rather than unconstrained optimization software, as you would do with NFXP, because NFXP always imposes the constraint. Okay. For the illustration of that method and for the illustration of many other methods, we're going to use the Zürcher's engine replacement paper, the model that is presented in the paper by John Rust in 1987, the optimal replacement of engines paper. Okay. So this paper, you really need to read in detail and understand all the bells and whistles of it, because we're going to use it as the test bed for all the different methods for dynamic discrete choice models that we go through. Okay. We use it for NFXP. We will try to estimate the model with MPAC, and we'll also try to estimate the model with other methods that I'll come back to later, like two-step estimation methods known as CCP type methods that we'll cover in lecture 17, and a refinement of that method called an estimate likelihood, where you do a sequential estimation where the conditional choice probabilities are updated. We'll talk about the details later. Okay, so in lecture 14, we'll go a little bit back to the applications of dynamic discrete choice models, and I'll focus actually on life cycle versions of this model. So these are models with finite horizon. And you can say it's not really a fixed point algorithm you need there because you solve the model by backward induction, just like you've done with your consumption saving life cycle models in the previous module. But the idea is the same. Where you want to estimate these models, there's an outer algorithm that searches over the parameter space and an inner algorithm that solves the model. So you can say that it's really NFXP that we are doing. Okay. So we can look at a few examples there. We go through a survey paper by Giri and Mira. And I'm going to focus on two of the references that they go through there. A paper by Anders Karlström about optimal retirement in Sweden, and then the career choice of young men paper by Keen and Volpin, which is about occupational choice in human capital. So the first is really just an application of Rust's model. In Rust's model, there's a bunch of assumptions that you need to impose in order to get it made tractable in 1987. Okay. Keen and Volpin relaxed some of those assumptions, and then they cannot really use the NFXP out of the box with these, or with a set of assumptions that is presented in the Rust and general placement paper, and we'll talk about how to relax some of those assumptions. Then in lecture 15 and 16, we'll go through something I'll call Surfer on steroids. Because you may think, who is caring about how the superintendent of maintenance, Harris Zucker, is replacing engines? It's a Mickey Mouse model from 30 years ago, and and there's just a binary choice in a single state variable. So who cares about Harris Zucker? And it's really a general framework, and in these two lectures, we're going to illustrate how this model can be applied to much more rich settings with several discrete choices, or that we'll look at with more state variables and more bells and whistles. It's also a model where we impose equilibrium. Okay, so let's take the first example, the paper with Christian Carstensen, Maria Juhl Hansen, myself, and John Rust and Fedor Ishakov, which is an equilibrium life cycle model of commuting, residential, and work location choices and house prices. In this model, there is a bunch of high-dimensional discrete decisions because you can live in many different regions of Denmark. Okay, so you discretize Denmark into, say, 100 regions. If you have 100 regions you can live in and 100 regions you can work in, you have like 10,000 combinations of those choices. And we'll look at how you handle larger models like that. And then it accounts for various family patterns and so on. So it's an equilibrium model, because if someone moves into an area, it's really putting demands on the housing stock. If someone is moving out in the area, it's supplying to the housing market. And so this model is a model where traders in the housing market meet, and in equilibrium, then the housing prices are determined, and then we estimate this model on the Danish register data. There's another paper we'll go through, which is about a durable asset market, the car market, where consumers, they choose what type of car to buy, how long time to hold it, and when to sell it on the secondary market. So it's a full dynamic programming model, or dynamic equilibrium model for the whole used and new car market. We'll go more into details when it comes to that. Okay. And then we go back to methods in lecture 17. In lecture 17, I'll cover a very important discovery by Hodson Miller in 1993 called the Hodson-Miller inversion. Their inversion theorem allows us to re-express the Bellman equation in choice probability space. Okay, so now we're used to look at Bellman equations in value function space, where you have basically a mapping. The Bellman equation is a mapping from value functions to value functions, and you search for the fixed point in that space to find the value function. Well, you can actually do the same thing with improbability space. And once you realize that, it's much easier, because then you can use this expression to formalize a pseudo likelihood, or you can put these predictions from the CCP inversion into your objective criterion that you're trying to minimize. So the short version is, you don't even need to solve the model by any iterative algorithm. You just go out and estimate the conditional choice probabilities and put them into the model, and then that indexes the beliefs of the agents, and the agent and the econometrician then only have to solve a static discrete choice model instead of a dynamic one. Okay. Now there's a lot of details here. We'll get to it, but this is the idea. Okay. And then Agirre and Mira, which is actually the paper we go through, they outline some very nice notation. They improve on that by making that estimator that comes out of it, it's a two-step estimator, so it's inefficient. They improve on it by allowing for some sequential updating of these conditional choice probabilities to make them, the structural estimates, more efficient. And in the end, if you iterate and iterate and iterate, under some circumstances, then it converges to the maximum likelihood estimator, which is fully efficient. So this is really a paper that allows you to trade off the computational cost of resolving the Bellman equation for each time you evaluate the likelihood function, and then the cursor dimensionality that is involved in non-parametric estimation of the conditional choice probability. So it's a trade-off between computational efficiency and then statistical efficiency, if you will. Okay, that's a lot of details. Okay, so this is all about only discrete choice models for single agents. Okay, so in part 4, we go to estimating games. Okay, and the goal is to be able to estimate dynamic games with multiple equilibria using microdata. But we'll start simple and build up like a stepping stone. Okay, so we'll start with static games with multiple equilibria, and we'll cover a paper by Qielin Su, which is about estimation of the discrete choice games of incomplete information, where he's applying a simple entry model. Now, this is the kind of paper that compares several different methods. He's advocating for the use of MPEG. So he's comparing the mathematical programming or equilibrium constraint that he advocated for in his Econometrics paper, 2002. And then he compares it with CCP estimators and nested pseudo likelihood NPL type of estimators, and he finds that MPEG is very reliable and very efficient. So we're going to compare also with the nested fixed point approach, which requires that you actually solve for all the Markov perfect equilibria of the game. And it turns out that if there's multiple equilibria, it is actually pretty important that you do that when you're trying to implement the maximum likelihood estimator. So we'll talk about the details there, but this is about comparing of estimators, giving an introduction to solving games of incomplete information and estimating them on microdata and various different methods that we have covered in our section on single agent models that we just went through, okay? Then we move on to an empirical application for a particular dynamic game that's here. They're not thinking about multiplicity of equilibria, which turns out to be an issue. And this is at Giri and Mira Econometrics 2007, where they consider an exit entry model in an oligopoly market using Chilean data from several retail industries. A very interesting paper. And so there we'll focus mostly on the empirical results and the interpretation of the results and so on. Okay, and then we'll move on to solving and estimating dynamic games with multiplicity of equilibria. Okay, now this is a big issue in I/O, that models can have several solutions. Okay, it's not like in the single agent case where if the Bellman equation is a contraction mapping, you have a unique fixed point. This means there's only one value function. Okay, there's only one set of conditional choice probabilities. This is not the case in games. In games, the set of player Bellman equations that is formulating the model can have several solutions. That can be multiple equilibria. So we'll go through first an example, illustrative example, based on a paper I wrote with Jan Rust and Fedor Ishrakov that came out in International Economic Review in 2018. Okay. Here we consider the dynamics of Bertrand price competition with cost-reducing investments. Okay. This is perhaps the simplest possible extension, dynamic extension of the Bertrand price competition model. Okay, Bertrand price competition is a unique equilibrium. It's like, you just price at the marginal cost of the high cost firm, if there's two firms. Okay. Now, you may want to consider what is going on in this market if the firms could potentially invest in the state-of-the-art technology that reduces their marginal cost. And this is should be a straightforward extension. But it turns out that this model, this simple extension, just gives a huge multiplicity of equilibria. In fact, in the versions of the model of the game that we saw, we found 1.5 billion equilibria. Okay, so how do you go from a model that has 1.5 billion predictions to learn about what equilibrium was actually played in the data? Okay, and that's where structural estimation comes in. The CCP's estimators would just assume that the equilibrium you observe is the one that was played, the single one that was played, and then you try to go out and estimate what was that. But in maximum likelihood, you would have to resolve for all these macro-perfect equilibria for each evaluation of the likelihood function. Okay. Well, the point is not for you to understand all this at this point, but to see that this is actually, this is close to being rocket science. It's really, really, really hard to estimate games, but there's hope in this course. You will learn how to do it because we have a surefire algorithm that can actually back out all those macro-perfect equilibria. It's called the recursive lexicographical search algorithm, or RLS. Came out in Restart in 2016 with the same set of authors, Ishrakov, Rust, and myself. And then we have another paper coming out where we're embedding this algorithm inside the nested fixed point algorithm in order to maximize, to estimate the structural parameters. We call that the nested or recursive lexicographical search algorithm. Anyway, at this point, probably, a little bit nasty to think about, but you will get there, and all this cool stuff you can do too. So I'm going to end here. This was just a plan, and then I'm going to continue in the next video on how to structural estimate this bus engine replacement model and go very much into detail with the nested fixed point algorithm. Thank you for watching.